another handout. It's kind of hard to see what's inside the chamber, so this is just kind of a cross section.
Thank you.
Thanks.
Sorry.
Thank you.
Yeah. No, we'll talk. We'll talk. Thank you, sir. Good to see you again.
Good to see you again. Right at the center of the diagram is where the substrate is held, and we have where the cells are material in 8 of those. It's designed for, the MBs are designed so I get great uniformity across the 3-inch wafer, and each of the cells has its own shutter. And it's because I have, for different compositions, I will only open and close certain shutters. I just want gallium arsenide. I only have the arsenic and the gallium shutter open.
So that's these here.
It's actually like here, and it's like a wagon wheel, and there's different cells here. I have the computer I program in, and I want these specific thicknesses with these specific compositions. And so what this is called, the Molly software we got from Pico. And what I do is I write a recipe and each of the steps. I can show you an example for this layer. The ones that are highlighted in green, those are the ones where the shutter is open. The ones that are clear, those I keep the shutter closed. So for this layer, I have silicon, aluminum, gallium, and arsenic open, and that would give me aluminum, gallium arsenide with a silicon also for it open.
So when you determine which element goes how deep, is that an empirical thing that you keep trying, or is it a mathematically derived thing?
I'll show you.
No, I mean, how do you know which one is going when?
How do I know? Well, I set each temperature to give me. I'll show you the next.
No, my question is more like, do you just keep trying different things and figuring out this works and this doesn't work, or do you say, well, we think we should put beryllium here and this over here and that over there?
We've done R&D on this.
Oh, I see. Okay.
Yeah, but we found actually through different tests to find out the right thicknesses, the right dopants.
Okay, so that part of it is experimental.
Those are all calibrated, yeah.
You keep trying until you get the best fit kind of thing?
Exactly,
oh,
yeah.
Okay.
Yeah.
But the element that you're going to use, you know that from other research, that we need to put aluminum or whatever else at this point.
Oh, yeah. Each layer is, and I can show you how.
So what's the success rate that you replicate what you've got here without impurities or?
Well, the impurities is once we get the chamber under ultra-high vacuum, we'll get good quality material. It's just a matter of calibrating the thicknesses and the dopants. When it's right, I can get within 1% or less than that.
And that's good?
Yeah,
that's close enough?
I can even get under 1%, yeah. For the vertical cavity laser, you need to be within 1% to get the mode right and
how are you making out on that anyways? The vertical cavity laser, you're still working on it?
We're working, we're having success with it, yeah.
Good.
Do you feel handicapped by not having a newer machine?
No, this is actually very good. It's an R&D machine, but it's actually a very good machine, yeah. We do, maybe once or twice a year, we do maintenance on it. We have someone come from Minnesota who's an expert at rebuilding this, and then we try to do it.
Put a new layer of tinfoil on it, that sort of
well, that's actually, that was something we do that actually actually under the tin foil is heat tape, and
Okay.
when you open it up, just the atmosphere will get water in.
Oh, okay.
So that helps to bake out the water. We do have somebody come in. Usually we try to do it around December, because we don't like to do openings in the summertime because it's so humid.
Sure.
That December is very dry.
Right.
And we've put new parts in and everything, and then we've had things rebuilt. And well, it's really once we get the good quality material, then it's just a matter of me calibrating all of these thicknesses. And the way I do that is on the other side of the machine, there's an electron gun. And what I do is I bounce it off the wafer at a very shallow angle, and it's picked up on a fluorescent screen. And when I open, say, a gallium shutter or aluminum shutter, what I'll do is I'll get it. It's sort of like it starts off bright and it becomes very dark and bright. It's almost like I was thinking of it like turning a flashlight on and off. And what I end up getting is a sine wave. And then when I use this software, it will give me a rate, and then I'll go into the program and use that cell temperature, and I know by the rate if I want to have, say for this layer 3,000 angstroms, I need 20 minutes or 20.5 minutes or whatever. And then the other cells, the dopant cells, we send out to a company in New Jersey that will calibrate that. Once those are set in stone. Those don't change at all.
So from a scaling or verification standpoint at the BAE facility, are they just larger 7-inch wafers?
Yeah, they actually have, they have ours is a 3-inch tool. They have a 6-inch tool. And
So they're, I guess, involved in just third-party verification at scale.
right, they have the bigger scale. I know eventually, BAE doesn't have. I know eventually that they're going to go to the industry will go to 8-inch wafers. That's something that.
How long does it take to do that?
This growth itself, our laser growth is about 7 hours long. Because I grow aluminum, arsenite, gallium arsenite, a mirror at the bottom. That takes a great deal of time.
So this part in here is about 1 hour, and this is about 6.
Right.
Okay.
Get a couple of different recipes through in a week, for instance.
Yeah.
Are there a lot of variations on that?
So once we have the growth set, I just use the same recipe. I might tweak from growth to growth. The cells can change maybe 1 degree or something, so I just have to recalibrate.
Once you have this, you've got the building blocks for each individual device.
Everything's in here.
Everything's in there.
Transistor, laser detector, modulator, everything.
Everything's in there. So this is the standard set.
This is it, from the growth point of view.
Okay.
But the different devices come about when you start the fabrication.
Right. Right. Okay.
Okay, so in terms of fabrication, we're going to go in here now and
Okay.